The goal of a research project was to design a diagnostic tool for assessing missingness mechanisms in healthcare datasets. Missing data is a common challenge in healthcare research, and the way that data becomes missing can have a major impact on the conclusions that researchers draw. However, it can be hard to determine why data is missing. Our tool helps researchers evaluate the type of missingness in their data. This would allow them to make better informed decisions and choose the most appropriate method for handling missing data. For example, they may choose to use imputation, delete rows or columns, or find more data. Choosing an incorrect method might affect the reliability of the dataset or introduce bias. There are three types of missing data. The first one is missing completely at random, or MCAR. In MCAR, the missing data is independent of observed and unobserved variables and is missing entirely randomly. The second type of missing data is missing at random, or MAR. In MAR, the data being missing depends on observed variables in the dataset. Therefore, we would be able to find a correlation between the variable that contains missing data and another variable in the dataset. The last type of missing data is missing not at random, or MNAR. This type of missingness depends on variables that are not observed within the dataset.
So why do we need to address missing data? Missing data is common in clinical healthcare datasets. Patients may miss appointments, there's lots to follow up, survey participants choose to skip questions, or healthcare records are incomplete due to documentation errors. The problem is that, as we now know, missing data is not always random. It can represent differences between groups of patients that aren't visible by simply looking at the dataset. For example, those who use substances may avoid questions on their frequency of substance use. If these missing values are simply ignored and not taken into account during the analysis, or handled incorrectly, such as using the mean to impute a value, the dataset no longer accurately represents the population, and we may misjudge the demographic. When these datasets are used to train AI models, the models learn from incomplete or biased information. This can lead to inaccurate predictions, reduced model performance, and unfair outcomes, particularly for underrepresented populations, possibly further increasing disparities. So being able to assess the missing data mechanism is an essential first step before choosing an appropriate method to handle missing values and developing equitable AI models.
And here's a demo of our tool. To get started, users can upload their dataset here. The tool then shows a preview with the rows and columns of the dataset so you can verify your data. For the first step, the tool runs Little's MCAR test to determine if our missing data follows a missing completely at random pattern. In this case, the p-value is significantly low, and we therefore reject the null hypothesis, confirming that our data is likely not missing completely at random. To dig deeper into why the data is missing, we can perform a shadow analysis. Here, the user can select columns with missing data, in this case glucose and disease type, and compare them against demographic columns like age, gender, and weight selected here. Once the shadow analysis runs, we get two tables. The first table answers the question, does missingness in one column correlate with missingness in another? Looking at the low Pearson correlation factors here, there is no significant correlation between missing glucose values and missing disease type values, so we can move on. The second table answers, does missingness relate to any of our observed demographic variables? For example, is glucose missing more frequently for a specific age group? If we look at the highlighted p-value for glucose and age, we see that it is statistically significant, meaning a relationship exists. To make sense of this relationship, the user can then view a dedicated plot of their choice. Notice how the average age in the group with present glucose values is significantly higher than the group where glucose is missing. This indicates that our missing data is missing at random, depending directly on age. Finally, as an extra bit of insight, users can visualize the overall distributions of the missing columns to further help make inferences. And that's how the tool helps you understand your missing data's patterns.